Everyone can still see my slide?
Yes.
Yes, sir.
Okay. No interruption, yeah? No connection problem, yeah? Now, two solid cylindrical rods, AB and BC, are welded together at B and loaded as shown. Okay, so the two parts are welded together at this point B here, at this section B here. And you have the loads or the forces here, 60 kilonewton, 125 and 125. Excuse me. 125 plus 125 together, you have how much? 250. Okay, 250. Now, knowing that the diameter of part 1, that means this part here, AB, is 30 millimeter, and B2, that means part 2, that is BC, 50 millimeter. Find the normal stress at the midsection of the rod AB, okay, the midsection of the rod AB, the midsection, and the rod BC here. Find the total deformation of the cylindrical rod AC. Then you have to find the total deformation of the rod of AC. Taking the Young's modulus to be 200 gigapascal. So that means there is only one Young's modulus. So that means the material is the same. Okay, we assume that is the same material throughout. So now, those of you have problem in our principle of superposition. So just take note now again, okay? Applying principle of superposition. So since, okay, it is shaded here as two portions, two parts, AB and BC. So just what we need to do is just split it up, okay, into AB and BC. That's what is given. So make things easier like this. It makes things easier. Okay. So just pick up this force here at the outer edge. At the outer edge here. Just pick up the force at the outer edge here. So and the force or the reaction at C here you don't know yet because you don't have any forces acting here in the diagram. So but then we have to first find out what is the force that is acting here. But actually, you can do it by taking the equilibrium of the whole assembly. So total left-hand force is 60. Total right-hand force, you have 250. So you can see there is a lag of 190. So therefore, the reaction at point C here should be 190 acting towards the left. But, okay, in order to present it onto your work, okay, on your working sheet, okay, what you can do is you just apply this principle of superposition. Okay, first take part AB as part 1 and section BC as part 2. And then pick up this force here, 60 kilonewton, and place it as section A here. So you have 60. So now, according to the principle of superposition, each part that you split it, okay, make sure every part must be equilibrium. So if this is 60 here, then this must be 60 as well, okay? So that is your section B. So when you look at section B, this is 60, but the original diagram shows you section B has actually 250 acting towards the right. But here at this section B acting towards the right, only 60. So when you consider the second part, that is section BC, okay, at the section B again, okay, what we have to do is we have to add whatever, okay, which is lag, okay. So here we have 60, but original that is 250. So that means you have to add in another 190 in the same direction as what is shown here. So this section B here of the first diagram, section B here of part AB, it shows that, okay, we have 60 kilonewton acting towards the right. So in order to get total 250, at section B here, I must consider a 190 acting towards the right as well. Acting towards the right hand side. Okay, so 190 plus 60, same direction, yeah. So you get the total forces or the total load of 250. So then you refer to the second part. Okay, so the second part here, okay, since we have this 190 for the equilibrium of this section, therefore you must have this 190 as well. So both the arrows is pointing in opposite direction, but the magnitude of the force is the same. So now, at section C, you have found out that, okay, there is a force, that is the reaction at this end here, 190 kilonewton. So that means from the principle of superposition itself, also you can find out whatever forces that is missing at section C. So once you have got your principle, once you have got your forces, okay, at each part, so we can find out the stress at each section of the bar. So first is the stress acting at section AB. So you have the force FAB, that is 60 kilonewton, okay, divided by the area. So this is 30, D1 is 30 mm, 30 millimeter. So we use pi d square over 4, or we use pi r square, okay? So if you use pi r square, it should be 15, okay? So I've used pi d square over 4, and then you have got the stress of 84.9 Newton per millimeter square. Remember, Newton per millimeter square can also be equals to mega Newton per meter square. So you can have mega Newton per meter square or Newton per millimeter square. Remember, 1 Newton per millimeter square is 1 mega Newton per meter square. And we got to know that this section or this part AB here is under tensile. Then when you refer to section BC, finding out the stress of section BC, so the same thing. So the force of BC, section BC or part 2, you have 190, but then you have to take note is compressive. This part is tensile, so compressive. So 190 kilonewton, you can put a negative sign beside the 190, okay? Or, okay, you can do whatever I've shown you here. By the end of the problem, or that means after the answer, you can write here compressive. Okay, if you don't want the negative sign here or the negative sign here. So you have to know that, okay, based on this diagram, we know that it is compressive. So you can write compressive. Or from the beginning itself, you can put then negative 190, and then you get negative 96.77. Okay, then also you can again change it to 96.77 Newton per millimeter square with the word compressive beside. Okay, then you have to find the deformation of section AB. So you remember this formula here, right? Okay, so put in your stress, your length, and Young's modulus. Okay, your stresses here is 84.9. So 84.9, yeah. So remember, this is in millimeter square. So make sure this everything here, this is also in millimeter. Okay, because this is in millimeter square. So this must be in millimeter. This also must be in millimeter. So 200 times 10 to the power 3 is 200 gigapascal. 200 to mega. 200 giga to 200 mega. So that means you have to times with 10 power 3. Why is mega? Or if you don't want to make it okay like that, okay, from the beginning itself, change everything here to meter. Okay, everything to meter, then you don't have the problem of, okay, putting in your E of 200 times 10 power 3. You can straight away just put 200 times 10 power 9. Okay, and then this one should be 84.9 times 10 power 6. Okay, this should be 0.9. Then your answer should be in meter. So this is the deformation that is found, that is 0.382 millimeter. Okay. Then for section BC, this should be BC. This should be BC here. Yeah. Hold on for a second. Okay. So this should be, sorry, this should be BC and BC also. Oh my goodness, what I'm doing. Okay, so BC. So the stress for BC is compressive 96. Okay, so that is why you see there's a negative sign here now, because you have to see this is compressive. So you can put a negative sign. And it's 6.77. The length, total length is 1.2 meters, so 1200 mm. So because this is in millimeter, so that is why everything I keep it as millimeter. So you get a deformation of negative 0.8, oh sorry, negative 0.581 millimeter. So remember, this is compressive and this is tensile. Elongation, this is elongation, this is contraction. So the next part, to find the total deformation, okay, so you have to add up the deformation of each individual section. So AB and BC. So AB is 0.382 positive because it's tensile. BC is negative 0.581 because it's compressive. So you'll get a net deformation of negative 0.2. That means the total deformation or the net deformation is still negative. That means it's still undergoing compression, okay, contraction for the whole bar itself. Okay, so hope you understand this part or this example here. Thank you.